Welcome, data engineers. Let's get started on mastering one of the most critical, yet misunderstood, concepts in Apache Airflow, passing data between tasks using XComs and the modern TaskFlow API. Welcome. Today we are tackling data passing. When you build data pipelines in Apache Airflow, it is absolutely critical to understand that tasks are inherently isolated. Whether you run them on Celery workers or Kubernetes pods, Task A and Task B do not share memory. So, how do they talk? As we see in the first bullet point, they use XComs, which stands for cross communications. Why do we need this? Because modern ETL requires dynamic workflows. If Task A downloads a file and generates a unique dynamic file path, Task B needs to know that exact path to process it. We achieve this by pushing the path into Airflow's metadata database. Now, here's the deep dive. XComs are automatically serialized into JSON and stored in the database. Because of this architectural choice, you should only ever pass small metadata like a string, an integer, or a URI. Never pass a massive gigabyte dateframe through an XCom. Let's look at this architectural flowchart. On the left, we have Task A, our extract task. Instead of talking directly to Task B, Task A writes its output directly into the central Airflow metadata database, shown in orange. Later, when Task B is scheduled by Airflow, it queries that exact same database to retrieve the information. This decoupling guarantees fault tolerance. If Task B fails and retries, the metadata is still safely sitting in the database waiting to be pulled again. Before Airflow 2.0, we had to manage XComs manually, and you will still see this heavily in legacy codebases. This is the explicit push and pull method. To do this, you utilize the task instance object, commonly referred to as TI. Inside your Python callable, you retrieve the TI from the Airflow context and explicitly call scom push, assigning your data to a specific key. Why use this old method? It actually provides incredible granular control. You can push 5 different variables under 5 different keys from a single task. To retrieve it downstream, the next task calls scom pull, specifying the upstream task's ID and the specific key. As a deep dive tip, if you are using the classic Python operator and you simply use the return keyword at the end of your function, Airflow will automatically perform an scom push for you under the hood, assigning it the default key name of return value. This sequence diagram beautifully maps the traditional XCom lifecycle. First, Task 1 executes its Python code and explicitly pushes a key file ID with the value 123 to the metadata DB. Time passes. Then, Task 2 spins up. Its very first operation is to reach out to the database and request the file ID specifically generated by Task 1. The database returns 123, and Task 2 proceeds with its execution. It is a completely manual, hand-coded handshake. Now, let's step into the modern era of Airflow, the TaskFlow API. What is it? It is a highly Pythonic framework designed to eliminate the heavy boilerplate code of traditional operators. The absolute basic building block here is the @task decorator. By simply placing this decorator above a standard Python function, Airflow magically converts it into a native task. Why is this revolutionary? Because it makes your DGs look exactly like standard Python scripts, radically improving readability. But the biggest shift is how we pass data. Instead of writing tedious ti.scom pull statements, you simply return your data from the first task and literally pass that output directly as an argument into the next task's function call. Our deep dive here is that TaskFlow is not replacing XComs, it is simply hiding them. The framework implicitly executes the scom push on return and the scom pull on parameter ingestion completely automatically. Let's trace the magic of TaskFlow in this code-oriented flowchart. On the left, we have a simple function decorated with a task that returns an IP address. You don't see any database code here, but the arrow shows the implicit XCom push happening automatically to the Airflow backend. On the right, the print IP task simply requires an IP parameter. Again, behind the scenes, TaskFlow performs an implicit XCom pull from the backend and injects it into your function. It feels like magic, but it's just brilliant engineering. Let's take a closer look at how TaskFlow simplifies dependencies. In traditional Airflow, you define your tasks and then explicitly chain them together at the bottom of your file using bit-shift operators, like Task A, Task B. TaskFlow eliminates this. When you invoke a decorated task function in your DG, it does not execute the code. Instead, it returns an abstraction object called an XComarg. By passing this XComarg directly into the next task function as a parameter, Airflow automatically infers the execution order. It knows mathematically that task B cannot start until task A finishes producing that specific argument. This prevents broken pipelines caused by forgetting to set a dependency. For our deep dive, what if a task needs to return multiple independent data points? You simply configure it task, multiple outputs equals true. You can then return a Python dictionary, and Airflow will unroll that dictionary, pushing each key-value pair as a separate, individually queryable XCom. This visual demonstrates the abstraction layer of TaskFlow. When we call getData, it sends an XCom arg to the DG engine. We then immediately pass that same variable into process data. The DG engine observes this data handover. The dotted orange box at the bottom shows the result. The engine automatically compiles the physical getData, process data dependency graph for you. You write pure Python, and Airflow builds the directed acyclic graph seamlessly. What happens when you need to mix the new world with the old? As a senior engineer, you will frequently build hybrid DGs. You might have a Python task that hits a custom API to get a dynamic table name, but then you want to use the traditional SQLite operator to query that table. The SQLite operator isn't a TaskFlow function. So, how do we pass the data? Traditionally, we rely on Jinja templating. Inside the SQL or bash parameter of the classic operator, we write a Jinja template using the double curly braces, ti.scom pull, specifying the upstream task's ID. When the task executes, Airflow renders the template, injecting the Python data right into the SQL string. Now for an advanced deep dive, in modern Airflow versions, the integration is even tighter. If a parameter in a traditional operator is marked as a templated field, you can actually pass the TaskFlow XCom arg directly into that parameter without using Jinja syntax, and Airflow resolves it for you automatically. Look at how the Jinja engine bridges the gap in this diagram. Our TaskFlow function on the top left returns the string users TBL. Our classic SQLite operator on the bottom left has a templated SQL string waiting for a value. At runtime, the Airflow Jinja engine intercepts the request, pulls the user's TBL string, and perfectly injects it into the SQL command. The final execution on the right is a fully formed, valid SQL query. This is how we orchestrate complex, cross-system data passing. Let's apply this to a highly practical, real-time use case, dynamic machine learning model selection. Imagine you are orchestrating an ML pipeline. You use TaskFlow to spin up 3 parallel tasks to train models A, B, and C using different algorithms. Once training finishes, each task simply returns its final accuracy score. Because of TaskFlow, these scores are automatically pushed to XComs. We want to automate our CI/CD, so we need the pipeline to pick the best model. We use the @task.branch decorator to create a branch Python operator. This branching task takes the 3 accuracies as input parameters. The Python code inside simply uses the built-in max function to find the highest score. It evaluates a condition, and then crucially, it returns the string name of the specific task ID we want to execute next. For example, deploy model B. Airflow reads this return string, executes that specific deployment task, and skips all the others. This is automated, intelligent orchestration. Walk through this dynamic ML pipeline with me. The 3 training tasks at the top execute simultaneously, passing their accuracy scores via XComs into our central decision engine, the @task.branch node. The branching logic analyzes the numbers, identifies 0.92 as the clear winner, and returns the instruction to deploy B. Notice the routing at the bottom. Deploy B is highlighted in green and executed, while paths to A and C are completely skipped. This logic all runs on the metadata passed seamlessly between tasks. We must address the biggest trap intermediate engineers fall into: XCom size limits. Your Airflow metadata database, usually Postgres or MySQL, is meant to handle small operational queries. It has strict size limits. MySQL might cap you at 64 kilobytes. If you attempt to return a massive pandas data frame from a TaskFlow function, you will massively bloat your database, lock up the Airflow scheduler, and crash your entire production environment. So, what if you actually do want to pass data frames easily? The expert solution is configuring a custom XCom backend. You can configure Airflow to use an object storage system, like AWS S3 or GCS for XComs. In our deep dive, here is how the architecture changes. When your task returns a data frame, the custom backend intercepts it, seamlessly serializes it, and uploads the massive file to S3. It then takes the tiny S3 //URI and stores that in the Postgres database. The downstream task asks for the XCOM, reads the URI from Postgres, and downloads the payload from S3. Total safety, infinite scale. Study this advanced architecture diagram carefully. When task A returns a massive 500 megabytes data frame, the custom XCOM backend intercepts the flow. Instead of hitting the Postgres database directly, it splits the operation. The heavy 500 megabytes payload is safely uploaded to cloud storage like AWS S3. Only a lightweight URI string is stored in Postgres. When task B needs the data, it gets the URI from Postgres, which tells it exactly where to go in S3 to download the massive payload safely. To summarize, mastering data passing in Airflow requires strict adherence to best practices. First, use the TaskFlow API by default for any Python workloads. It vastly simplifies dependencies and makes your code beautiful. Second, the golden rule: keep XCOMs small. Pass metadata, file paths, and business dates. Do not pass raw data. Let the downstream task use that path to read the data from cloud storage. Third, implement periodic cleanup of your XCOM tables. Orphaned XCOMs will slow down your database over time. If you absolutely must pass heavy objects natively, implement an object storage custom backend. Finally, remember that because TaskFlow relies on pure Python functions, you can unit test your business logic locally without even booting up an Airflow instance. Thank you for joining this masterclass. Please invite your colleagues to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. See you next time. This final mind map solidifies our core concepts. Airflow data passing relies on the synergy between the TaskFlow API and XCOM metadata. TaskFlow provides the clean code and auto-dependencies, while the XCOM system mandates that we keep payloads small by passing URIs, or by offloading heavy lifting to custom S3 backends. Adhering to these principles guarantees highly resilient data architecture.